today's recap video, we will have an overview of the different types of perturbations one can make to metabolic networks and how we can set them up as optimization problems. And now, how do we go about perturbations, right? That is the immediate next thing to start worrying about. So, how do you perturb the models? So, what kind of perturbations did we look at? Reaction, deletions, synthetic lethals or multiple so you can also delete genes, and lastly overexpression. Now, let us just stop for a moment and think back what happens, how do you simulate each of these, right. You basically start with the original flux balance solution formulation, right, which is this, and plus what do you add to this? For a deletion, how do you simulate a deletion? So, add an additional constraint saying V d equals 0, right, or let us just say V k equals 0 for some reactions that we want to delete, for a single reaction or multiple reactions, right. And let us say the solution here is going to be V d, right. So, it is going to be the same thing, max C transpose V such that S V equal to 0, additionally V k equal to 0, right, and this will give you a solution V d, right. What happens if it is an essential reaction or it is a lethal phenotype? Right. So, one thing we did not think about so far is, should you always be able to solve this? What does the system look like? So, it is a linear system of equations with potentially infinitely many solutions, and you are adding some additional constraints and you are maximizing a linear objective function, right. So, are you supposed to be able to solve this always, or are there scenarios where you may not be able to solve it? So, think back for a moment to the Cobra toolbox or to LinProg, right. Was there something of importance there? How did we call LinProg? We would have called LinProg something like X is that right, something of this sort, right. So, this is nothing but your V, this is nothing but your, this is your exit flag. Did my simulation or LP complete or solve, right. This of course does not exist for us, basically use blanks, this is S, this is V, this is LB UV and this is C. So, everything fine so far? Any doubts? Okay. So, will this solve or not? Will this always solve?
No, sir, if you. The new constraint lies outside allow equal.
What kind of constraints are we imposing? Are we imposing constraints that may break the system, or it's not a big problem? So, one thing you need to immediately see here is that V equals 0 is a perfectly valid solution. It's not an interesting solution, but it's a trivial and practically always existent solution, except if you have certain lower bounds. So, if some of your LBs are greater than 0, infeasibility may occur. Classic example for this, ATPM. So, very well, this becomes a tricky scenario now. You may have to find out that you have an infeasible solution and therefore conclude that it is actually a lethal phenotype. See, normally we conclude that there is a lethal phenotype only if you get a 0 solution, a 0 optimal solution. So, like my maximum growth rate possible is actually 0, right. Whereas, in this case alone you may have infeasibility which will lead you to conclude that clearly I could not make my ATP, I could not make enough ATP that was required for survival. So, I have an infeasibility, hence lethal phenotype. So, this is something to remember.
But the ATP maintenance, if it's not being able to meet it, then automatically biomass will be 0.
Biomass will be 0, but there are cases where you will not be able to. So, you are saying that LB is 8.3, right. Maybe I am not able to get LB of 8.3. So, I will actually be, it will be infeasible. So, if constraint is not satisfied, then you do not even have a solution. If your constraint is satisfied and you get a 0 solution, it is a different story. If your constraint is not even satisfied, then you have a different problem, which is what I am trying to emphasize here. It depends. So, sometimes if that constraint is satisfied and other constraints are not satisfied, then you will get a fair and square 0 and lethal phenotype. There are scenarios where it is like saying solve x plus y equals 5, right. So, x less than and give it some infeasible constraint, and you say that x greater than 10, y greater than 10. You can never solve this, right, you will get an infeasible solution. So, while at perturbations we studied alternate formulations, right. So, let us say FBA is already one formulation, we then studied minimization of metabolic adjustment, room, and then for overexpression we studied FSEOF. You can also use MOMA to study overexpression or anything else basically, right. So, what is MOMA, right. We now said that it is not very fair to say that the objective function must always be growth maximization, because there are cases where clearly the organism may not be able to sustain maximal growth, example under several gene deletions or even a single gene deletion. So, in that case we said, let us say Vd is your new vector flux distribution and Vw was an original flux distribution. We said we will minimize this, of course subject to LBs and UBs, right. So, this became a quadratic programming formulation. Room came up with an MILP by trying to reduce the L0 norm of but it had some additional variations, like it had 2 parameters delta and epsilon that could be varied and so on and so forth, right. But essentially these were different takes on the same constraint based formulation without using FBA or the maximum growth rate objective function of FBA.
So here MoMA B can be B will be less different, but the new biostar can be minimum can be lesser than what it could be.
So the new biostar is also as close as possible by definition to the original one.
We cannot tell that for sure.
So you're trying to keep the vectors as close as possible. So the biomass can change, but you're trying to keep the fluxes as close as possible.
Yeah, so whatever biomass star we are getting may not be the maximum which we might have got if we are not minimizing.
True. But the idea is this is going to better capture what the cell is doing. So now let's look at how would you use MoMA to fit fluxes. Right, we did discuss that briefly. So it becomes very similar, right. So if you look at the quadratic programming formulation, it will look something like half this was the canonical quadratic formulation, of course subject to SV equal to 0 and this whole stuff, LBs and UBs, right. We then said that this matrix will change if only partial data on flux measurements are available, right. This is something I want you to verify, but now let us just do a slightly different problem. How would you simulate overexpression with MoMA? Or before that, how do you even simulate overexpression?
Increase the lower bound.
So you basically solve first and you get a wild type flux, and now let us say some Vk equals some alpha, right. Now reconstrain, right, Vk greater than equal to 2 alpha and run the same old FBA formulation. Right. Or you can go in for MoMA. How would you do MoMA in this case? It is just identical to this, except you have a different set of constraints. You have, instead of these constraints, you have an additional constraint that Vk greater than equal to 2 alpha, and of course you again run the risk of infeasibility, right. Because anytime you leave out 0 from your solution space, you have a possibility that the solution may not be feasible.
So how will you run MoMA?
How will you run MoMA? The same way, right. You have a flux vector, initial flux vector, right. You have a new flux vector Vd or Voe, and you now minimize the distance from this flux vector and the original flux vector subject to the new constraints. So subject to all these SV equal to 0 usual constraints, and additionally ask for Vk greater than equal to 2 alpha. So if Vk is greater than 2 alpha, what is the nearest space? So let us see if we can capture it geometrically. let us say this is VW, right. So, now I am saying find something here, right. Let us say this is, so Vk, sorry, this Vk and let us say Va or something. Now I am saying that, let us draw it more correctly. Okay, so this is some alpha and this is 2 alpha. Now I am going to say that Vk is greater than 2 alpha. So find the closest flux that agrees with other constraints, maybe there are other constraints like this, whatever. So find the closest flux using MoMA. So if you remember, if we actually had constraints like this and so on, MoMA essentially looks in circles around this, right. These are contours where Vw minus Vd is same. Out of all of these, which of these cuts my new constraint? Let us say these are my new constraints. And so maybe I would put this as the new optimum. So is this all coming together nicely, right. So you can see how flux balance analysis and related techniques can be used across a spectrum of situations. So in today's video we started off with perturbations and we will continue with perturbations tomorrow as well, building on what we studied about dilutions and so on towards synthetic lethals and FSEOF, which is used to study overexpression.